the University of Bielefeld, and he's going to tell us about 3D vision and interactive disambiguation for grasping.
Thank you very much for inviting me to this very high-profile workshop. So at Hashke in Bielefeld, we try to develop cognitive technology which facilitates human robot interaction or human technology interaction in general. So that includes, of course, motion intelligence. We are dealing with hands. I want to understand grasping and manipulation. We develop tactile sensors. We monitor human manipulation motions with a set of lighting cameras. We study child learning. We consider interactive dialogue. Attention is, of course, a very important topic. We developed this Toby head, which allows for emotions, robot emotions, and we are also studying biology concerning insect-like walking, for example. However, the focus of the work in our group is on hands. We want to understand human hands, replicate that facilities, these manipulating skills in robots. And to this end, of course, we first need to recognize the objects we want to deal with. So that's a vision workshop here. And I want to introduce our approaches to segment the scene into interesting objects. And here we follow a approach which tries to avoid a lot of object or word knowledge. So we want to deal with unknown environments. So we try to follow model-free approaches, both for object recognition as well as for task planning. And first of all, so we developed a real-time segmentation approach to deal with these very cluttered scenes, as you see there. And to this end, we focus on depth information. So if you use color, that deals typically to over-segmentation. For example, if you can consider this very highly textured cylinder. However, if you, on the right side, consider the surface normals, they very, very smooth, and you yield very smooth surface regions, which can be the basis for segmentation. However, of course, color is important, and there are algorithms to derive depth from shading, for example. So it's useful to consider both, but we do that hierarchically in the very first step. Often consider depth, and then for recombining surface regions, we also consider color. And as you see here, there's not always depth where you might expect it. So it's useful to use depth information directly. So our segmentation algorithm can be split into phases. In the very first phase, we try to come up with these smooth surface patches, having a pipeline of some filtering to smoothen the connect information, then computing the surface normals, and finally the object edges, which are regions of the image where the surface normals have a very sharp change, or there's a heavy step in distance. And finally, we can use a simple picture drawing algorithm to come up with this, these surface patches. Finally, we need to group these surface patches into potential object hypotheses. We are combining this over-segmented scene into these object hypotheses, and to this end, we compute a connectivity graph, as you see on the right bottom, of potential connections between these surface patches, and then we apply a simple graph cut, cutting between 3 and 6, to come up with the correct groupings to form So let's have a look, closer look into this second phase, how we compute this connectivity graph. To this end, we use three simple heuristic rules. The most important one is the cut fields of surfaces. So if two surfaces should belong to the same object, they shouldn't cut each other. So we look for pairwise, consider these pairwise cut freeness of surfaces. Here, surface 7 and 11 cut each other, they belong potentially to the same object, so we establish a link. However, surface 11 cuts the surface 12 into two pieces, and they shouldn't belong to the same object. So no connection is established, and you can do that for all the potential surface pairs, coming up with a very good initial guess for object hypotheses which are related or associated to strongly connected subgraphs. However, as you see here, there's no connection between these object paths 2,8 and 5,3, which actually should belong to the same object. And to resolve these problems, we added two more heuristic rules which try to realign surface edges with as alignment as possible. For plane sets, very easy. You can simply check the coplanarity of two planar edges, and to deal with curved surfaces, we consider normal histograms on the next slide. And of course, we need to check also whether these surface edges are actually separated by occlusion. So surface 7 and 4 here are nicely aligned. It could be merged into a single phase. However, they are not separated by occlusion. Should be combined for this reason. So finally, we compute connectivity weights to come up with a weighted graph, which then can be used for graph cuts to compute the cutting costs. And here we simply use uniform weight distributions, assigning weights 1 over n, where n is the number of outgoing edges from each node. And as you see here for node 1 and node 3, there might be different weights depending on which node you consider, and to come up with symmetric weights, simply average them, which then gives this node, this final graph. And cutting this edge here between 3 and 6, which has a lowest weight, we come up with the correct solution as we have seen before. And of course, there's a huge potential for further research to adjust those weights to come up with better solutions. So we could include confidence results from our matching steps. We can include color matching to recombine based on color. We could consider the Euclidean distance of surfaces, so far away from surfaces maybe shouldn't be merged again, and so on and so on. And to give you an overview of how we merge curved surfaces, that is shown on this slide. So first we compute so-called normal histogram, computing simply the histogram of x, y, normal components into this by-variable histogram, normalizing it. And it turns out that these histograms are very specific for the particular object surface shape and orientation. So if you consider, for example, this horizontal cylinder here, it creates a vertical line in this histogram because all the surface normals change along one axis only. And if you consider the vertical cylinder here, this bottle, all the normals change in a different direction, but again along one axis, so we yield a line which is now horizontally. So comparing these histograms, now we can judge the similarity of these surfaces and then reconnect them if they could be aligned. So looking at the results, there's a nice 3D segmentation database provided by Markus Lynch's group and Tiovina. And as you see from these results, we have very competitive segmentation results, 96% correct segmentation. So Markus Lynch's group is slightly better in segmentation. However, they are not as competitive as we are regarding processing time. So we are the kind of only work which can be computed in real time, which is very important for us because we don't want to deal dynamically with dynamically changing scenes. So to get an impression of this database, there are some examples of simple boxes, stacked cylinders, getting to more complex scenes, and in really complex scenes very degrade them in performance. Here you see that segmentation results get worse. So for example here we cannot merge two surface parts of the bowl, or there's a small patch of the table here associated to this link button. Oops. So the next step is, of course, to classify objects in order to talk about them. And to this end, we use simple neighbor classificator acting on the back of features. So we have three features, two considering the shape of the object, considering the elongatedness, the ratios of largest and smallest eigenvalues, the volume of the shape of the point cloud, and comparing colors and mass. And this gives us scores which are here normalized to a range of 0 to 1. And you can obtain the final score using the minimum of all these individual scores, which kind of ensures that all the features need to match for good matching, and avoiding the problem that a single good matching feature can somehow outweigh not so good matching features. So additionally, we have classifiers for individual object attributes like color and elongatedness, so that we can talk about these attributes within a disambiguation step now. So if we want to grasp and deal with objects, we need to refer to exactly one object, and if there are several similar objects on the table, we need to resolve these ambiguities, and we do that by asking for the most informative attribute. So we have these absolute attributes, EMC in the class label, color and elongatedness, and some relative attributes which always consider only two objects, namely left, right, front, back, and small group. So what is the usefulness of an attribute? First, we want to ensure that the attributes of different objects are different, so there should be a high inter-attribute entropy. And within a single object, the entropy should be very low, so we shouldn't ask for color, for example, if an apple is yellow and red, because that doesn't make sense.
Show me the apple.
Okay, so a lot of theory, that's a video illustrating that much better. So in the upper left corner you see the view of the robot highlighting object hypothesis.
Show me all bananas.
And now the robot always highlights
Show me the globe.
resolved objects in this image. We can evaluate pointing
Show me
gestures,
this atlas.
evaluating this from the verbal input,
Show me the atlas.
using the
Green or the orange.
timestamp of the last observed pointing gesture.
Can you point at the apple?
This one.
Over there.
And that works quite nice to resolve these objects. So currently you are working to extend that towards a hierarchical segmentation tree, which is mainly motivated by our intent to also identify object parts, but also due to the problem that it's difficult using the graph card we used so far with a fixed threshold to find the right level of grouping. So you need to adjust this cutting threshold correctly to come up with a correct grouping level. So the idea is quite simple. We simply iteratively apply the graph cut, always finding the minimal cut into two subgraphs. So here, for example, first cutting off the handle, splitting the outer and inner surface of its mark. And then we get this hierarchy of grouping hypothesis with the more loosely coupled groups at the top of the graph and more strongly connected groups at the leaves. And if you now apply our classifier in top-down fashion, we can nicely find the correct level of grouping. So if the classifier already succeeds considering the whole point cloud, here detecting a cup, then we could stop. If not, we could further proceed to smaller components, smaller point cloud blocks until we find the correct level. Or we can always proceed to lower levels, and then we will find all the object parts if they are trained within the classifier. So how we can now use that information for grasping? We don't apply these classical grasp planning approaches, having a full-fledged mesh available on the objects, and then doing a lot of simulation to come up with grasps. However, we also need to somehow estimate the size of the object, which is typically difficult because we only have one view of the objects. So we use superquadratic splitting to fit very simple geometric primitives into these point cloud blocks, and then classify them into series of cylinders, which then is used to choose one of three graph prototypes, namely power graph, transition graph, and pincer graph. We need to align our hand, of course, to the object, but this major X object can also nicely be extracted from the point cloud, and then we can simply approach the object grasp using force feedback, here using the tangent forces provided by the shell net. So I guess there's a video as well. Showing now grasping of the object. So we fit here a sphere into this ball, and because it's a sphere, we don't need to care for orientation. We can simply approach the object from any orientation, and then grasp it, hand over at an arbitrary position, and there's again some interactive dialogue to arrange for the hand over. We can also apply that approach for more complex manipulation motions. So presented several years ago at humanoids, where we trained a neural network to mimic human screwing motions, which are then simply applied in a free-falling fashion to this robot. Of course, in this video that worked quite nice. However, in practice, it's rather difficult if you don't have visual or tactile feedback. We apply either too much force or too less force, not rotating the cap anymore. So there's a strong need for tactile sensing and tactile integration in robotics. And we developed a whole zoo of different tactile sensors. One of the first being this square modular flat sensor here. All the sensors use the piezoresistive principle, and this particular sensor here provides a good spatial resolution of 5 millimeters and a very high frame rate of nearly 2 kilohertz, which is then suitable for slip detection. So slip occurs, or a slip induces micro vibrations in a 400 hertz range, and if you can detect those vibrations, you can estimate slip. And as you see in the video, use that estimation to increase the grasping force to hold this object of changing weight. Of course, the sensor is too large to be fitted into a robot hand, so we try to miniaturize our sensor and shape it into a nice fingertip form, and to also cover all the other segments of the hand, and as well the palm. There's not much room in typical robot hands. We use a different sensor technology using conductive fabrics. So we have a very thin and flexible tactile sensor available. And you see that here on the shadow hand, it is like having all these sensor patches and flash. And on the right hand side, you see all the tactile sensors available now for control. So you can use tactile information for control. Of course, we can simply apply visual algorithms to come up with some important tactile features like contact position, the normal force, or the orientation of an object edge, which is visible on the tactile sensor. And then we can use tactile controllers to map errors on these features directly on sensor motions, and use inverse kinematics to come up with appropriate joint motions to realize these sensor motions. So we use here, or we came up with 4 tactile control primitives. First, to control the contact position, we can move the sensor tangentially, of course. We can move the sensor in normal direction to apply correct force. That's another motion here to realize contact position control, now rolling the sensor across the surface. And finally, we can rotate the sensor in order to align the object edge. And if we combine all these primitives and add an external motion component, we can now realize explorative motions here, tracking this cable, which is completely unknown to a robot, or explore the two-dimensional surface of this bottle, which is also completely unknown to the robot. So what are our future directions? We want to, of course, compare now the control methods which we have originally developed for the simple quadratic flat sensor to the sensors which are now available in the hand. So that's on very recent work we did at the beginning of this year. And we started at Cytek a similar project to Angelo Canzalotti's work, trying to learn about object properties using autonomous exploration, human imitation, and interactive dialogue to learn the meaning of objects and actions. So thank you very much for your attention.
How do you think the alignment of the